In this video, we'll consider the electric field due to a dipole. A dipole is when you have two charges of opposite signs, say a plus Q and a minus Q, separated by some distance. That distance we'll call D. So I'm going to take the origin halfway between the two. So this one's located at x equal d over 2, and this is located at x equal minus d over 2. And I'm going to look for a point for this particular problem along an axis of symmetry. That's what I'm called the z-axis, midway between the two. There can be other problems assigned. You could be asked to find the electric field, for instance, over here, or electric field over there. You could find the electric field over here, but then the math gets extremely more difficult, and it generally is not one that's assigned at the university physics level. So we'll do the one right here in the symmetry. So what we need to do to find the electric field is find the electric field due to each one of these point charges. So this electric field here, we've got a distance r going up like this. I'll call this r1. And of course it'll have a unit vector, r1 hat there. And then for the other charge, its distance goes this way, at least best as I can draw a straight line on a computer. And that's r2. And it of course has a unit vector that points this way, which is r2 hat. We'll need some angles. We'll be interested in this angle here, this theta, which is the same as that angle there, theta. Two parallel lines cut by a transversal. Alternating interior angles are congruent. And likewise this angle here, which in our case is also theta, is the same as that angle there. To find the electric field, it's due to the electric field on the from the positive charge, E+, plus the electric field due to the negative charge. This is going to be equal to K times Q over R2 squared times R2 hat. And the other one is minus K Q over R1 squared R1 hat. In this particular problem, the geometry is such that R2 is equal to R1 and is simply the hypotenuse of a triangle whose length is Z and whose other side is D over 2. So it is equal to the square root of D over 2 squared, that's one side, plus Z squared. And we'll just call this R. To find R1 hat, well, to find R1 hat, we need to write R1 hat up here in terms of this triangle. We have a cosine theta I hat and a sine theta j hat. So R1 hat is cosine theta I hat plus sine theta j hat, which is equal to the cosine can found easiest by looking at this thing here. That's this side, which is D over 2 divided by the hypotenuse, which is R. That's a hat. And then sine is found by this opposite side, which is Z over R j hat. And likewise, doing the same sort of thing, but noticing that for R2 is in the negative I hat, positive j hat. We have that the R2 hat vector is minus cosine theta I hat plus sine theta j hat. And that gives me minus D over 2 R I hat plus Z over R j hat. Now what we want to do is we want to put this information into the equation here and simplify it. So the electric field is equal to, I've got a K, a Q, Both of those are the same on both sides. These R's, R2 and R1 are the same. They're R over R squared. And then for R2, I plug in minus D over 2RI hat. And plus Z over RJ hat. And then for the minus R1 hat is minus D over 2 R I hat and minus Z over R J hat. And we can see that the J hat terms cancel, while the X terms, the I hat terms, add together. So now I have the electric field is equal to T Q. A minus D over 2 and a minus D over 2 makes a minus D. The R I can combine with the R squared here, and so I get D minus I hat over R cubed. Now here's something that people notice in these type of problems involving the dipole. The strength of this field E always depends on the product of Q and D, the charge and the separation between those two charges. So they have decided to create a vector that they will call P. And that vector will go from the negative charge to the positive charge. So let's draw that on our diagram. So coming up here, let me put a new vector arrow, and it's an arrow right along here, and they call this P. And P goes from in the positive I hat direction in our case, and its magnitude, its length, is not the total distance between here. Maybe I kind of misrepresented by doing that. It's not this distance. It's D times Q. But at least I wanted to show you the direction that it points. So P is defined in terms of the magnitude as QD and points in direction from minus Q to Q. And there's the magnitude and there's the direction. So what's usually done is that direction, this direction here, is given to this D. Now if we look at that, our solution here isn't that. It's K, there's the magnitude P, but the direction is the opposite of this direction. It goes in the minus I hat, not in the plus. So our formula now can be written more compactly as minus K P vector over R cubed. Now what is P? P has a name. It's called the dipole moment. So that's one thing to note. The other thing is we actually have our answer to our problem. And there's some important things to note about the answer to our problem. So I want you to note some things. Note, the dipole field goes as 1 over R cubed and not (1 over R squared), as for the point charge. This is something anyone would expect you to know about dipoles. They're weaker in terms of when you get further away than is a straight point charge. But even if there's no net charge, as there were in this case, if the charges don't lie right on top of each other, there can still be an electric field. And this happens often when you have some set of charges near a material like water, and you can create a dipole moment in the water. Or you can create a dipole moment by displacing, for instance, the electron cloud with respect to the proton. So it's a very important problem that we have. Now let's finishing this off, let's go back and just take a look at our problem here. We had this minus Q, we had this plus Q, there was some distance Z, and the electric field pointed this way. And if we wanted to write that in terms of our other variables that we had in our problem, we could have written it as E is equal to minus K Q D I hat, and in our R cubed we had D over 2 squared plus Z squared to the 3/2. And then you could plug in numbers to work the problem. But we generally tend to prefer to write things in this form because often Z is much, much greater than is the distance D. And so we'll talk more about those type of problems and approximations in the next video.